Right, so now that we've got our single bonds in there, next thing we're going to want to do is create double/triple bonds. So we can't have more than triple bonds, never draw 4 bonds. Or, quadruple bonds to do 2 things. The first thing we want to achieve is to fill octets. Remember, that's more important. And then the second thing we want to do is minimize formal charge. Raise that out of the way. All right, so we're going to achieve step 1 first, right? We're going to give everything an octet first, and then we'll worry about formal charge. Where are these electrons coming from to make these double and triple bonds? The electrons come from the lone pairs. So they're going to, we're going to take lone pairs away and turn them into double and triple bonds. Remember that period 2 elements, so our carbon, nitrogen, oxygen, and fluorine, can't have greater than 8 valence electrons. No matter how much it would help you to minimize formal charge, they cannot have more than 8 valence electrons. Everything else, though, can. So period 3 and below can have more than 8 valence electrons. So if we need to have it more than 8 valence electrons in order to minimize formal charge, that's totally fine. Right, so our first objective is to give everything octets. Next thing is to try to minimize formal charge. So in general, lower formal charge is better. If you do have a negative charge, which we will pretty often, we want to put it on the most electronegative atom. Right, and that makes sense. The most electronegative atom wants the electrons the most. So if we're going to put a negative charge anywhere, we might as well put it on the one that wants the electrons. And then there's a third thing to consider, and that's you have to ask yourself is, did you make any arbitrary decisions? Did you turn a lone pair into a double bond for no other reason than you wanted to? I mean, I'll show you examples here shortly. If you did, that means that resonance structures exist. That's kind of a confusing statement, but when you see some examples, I think you'll get it. Cool. Through the magic of technology, we're going to go ahead and just paste what we did before. And then through the further magic of technology, we're going to space it out. If you're writing this in your notes, you can, rewrite it, write it on the same thing, whatever you want to do. Then notes are there to help you out. I don't like assigning busy work. I don't think anything that I sign is busy work. I think everything that I sign has a purpose. So, do what's best for you. I'm not like that super strict on it. The idea is for you to learn the content. All right, so let's go ahead and take a look at this carbon dioxide. First, we want to ask ourselves, what doesn't have an octet? And what doesn't have an octet is that central carbon. It is 4 valence electrons short. So what we can do is we can take this lone pair and turn it into a double bond, and take a lone pair from the other oxygen and also turn it into a double bond. The structure we get is that one right there. And then if you calculate the formal charge, I'm not going to do it, but you can go ahead, pause the video and do it yourself. All of our formal charges here are equal to 0. So that's a really good resonance or a really good Lewis structure. Everything has a filled valence shell and everything has a formal charge of 0. Note that I pulled electrons or pulled a lone pair from each oxygen. What if I pulled 2 lone pairs from one oxygen? Well, then the structure you would get would be looking like this, right? You'd have a triple bond on one of the oxygens, and then a single bond on one of the other oxygens. And then when you calculated the formal charge, what you'd find is this oxygen has a positive formal charge. This oxygen has a negative formal charge. And so remember that we want to minimize formal charge. So this resonance structure is not as good as the one on the left. So the one on the left is the more correct resonance structure. So again, a lot of this comes from practice and feel and that kind of thing. This one here, we would just want to go ahead and calculate any formal charges. If you think about the central nitrogen, we already did that one, right? This central nitrogen has a +1 formal charge, so we'll just put a plus there. We don't have any lone pairs to make double and triple bonds. We note that our ammonia also has a +1 charge, so we have to put that formal charge somewhere, and it goes on that nitrogen. There's really no other way to do it. Down here on our CH3 OH, everything has a filled valence shell, right? The oxygen carbon have 8 valence electrons, the hydrogen have 2. Everything's happy there. Next thing we want to do is calculate the formal charge of all of these atoms. Go ahead, pause the video, do it yourself. Cool, good job pausing the video and doing it yourself. Hopefully you actually did it and not lying to yourself. All of the formal charges are equal to 0. So that's our structure for methanol. All right, next up, we're on nitrate, right? So we notice that the nitrogen is short 2 electrons or 1 bond from having a filled valence shell. And so what I need to do is I need to pool electrons from one of these oxygens to make a double bond. However, when I do so, I'm making quite an arbitrary decision, right? I could pull them from this oxygen. I could pull them from this oxygen, or I could pull them from this oxygen, right? That central nitrogen only needs 1 more bond to have a filled valence shell, so I don't want to do it from all 3 oxygens. So how do I decide which oxygen to do it from, right? I can draw all 3 structures and think about which one is better. So let's draw, right, this one right here with a double bond. What if I made the double bond in the bottom left? Or I guess that's the bottom right, huh? Or what if I made it in the bottom left? For real this time. We'd want to determine which one of these is the better resonance structure, right? So next thing we want to do is calculate formal charges everywhere. Go ahead, pause the video and calculate the formal charges. Hopefully you actually did that. You'd find that the nitrogens have a positive charge, and then all of the singly bonded oxygens have a negative charge. So what we can tell is that all of these are the same. Or all resonance structures are equally good. Or all structures are equally good, right? Because I made an arbitrary decision. There was no reason for me to pick either one of these oxygens. I just picked one and drew a structure, or in this case, I drew all 3. Whenever you make that arbitrary decision, that means that you have resonance structures. And so these 3 are indeed resonance structures, and they're all equally good as one another. Note that the formal charges sum to equal the overall charge. Right, our nitrate has a charge of -1. And then if you think about the nitrogen, it's +1, and then we have 2 negative ones. So you sum those all together, you get -1. Maybe you're thinking, well, wait a second. If I just take a lone pair from this oxygen, I move it down to make another double bond, that will minimize the formal charge even further, right? Nitrogen would then go to a neutral formal charge, and so would that oxygen. Anytime you create a bond, you get kind of closer to 0. Why can't you do that? Well, remember, nitrogen cannot break the octet rule. So we can't minimize the formal charge any further. If it was something other than nitrogen, something period 3 or below, totally valid move. It's nitrogen, can't do that. So we can't minimize the formal charge any further. Nitrogen can't have more than 8 valence electrons. And then if you think about the bond order here, go ahead, pause the video and calculate it. What is the bond order of the real compound? The bond order is 1 1/3, right? So again, it's not that some of these bonds are single bonds or double bonds in real life. It's not that the structure is alternating from one structure to another. It's that it's a combination of all 3 structures, or an average, or a hybrid, however you want to think about it. And so that bond order is 1 1/3. All right, let's go to H2SO4. So again, go ahead, pause that video, and then calculate all the formal charges. Hopefully you did that. If you did, what you'll find is that this sulfur has a formal charge of +2, and this oxygen, the top and the bottom oxygen, have a formal charge of -1. Note that everything has an octet. I probably should have said that first, so we don't want to create any double or triple bonds to fill octets, but we do want to create double and triple bonds to minimize formal charges. In this case, sulfur already has 8 valence electrons, but sulfur is a period 3 or below element, and so it is allowed to break the octet rule if it would result in lowering the formal charge. So what we can do is we can take this lone pair and create a double bond. Note that that oxygen is giving up electrons to form a bond, so its formal charge is going to be reduced. It's going to go from -1 to 0, and then the sulfur will go from +2 to +1 because now it's gaining electrons. And then we can do the same thing with this bottom oxygen as well. That'll also reduce the formal charge of both the oxygen and the sulfur. So then the final compound that we get is this one right here. And there's our Lewis structure for sulfuric acid. Note again, the sulfur is breaking the octet rule, but if you calculate all of these formal charges, they're all equal to 0, and sulfur is a period 3 or element below, so it is indeed allowed to break the octet rule. All right, so let's go ahead and take a look at our acetate compound. So if we think about what doesn't have a filled valence shell, it's going to be this central oxygen right here. It does not have a filled valence shell. And so what I could do is I create a double bond to fill that valence shell. Well, where could I get the lone pairs from that double bond? I could get it from this upper oxygen, or I could get it from this lower oxygen. Is there a reason to pick one or the other? No, the oxygens look exactly the same. So I'm making an arbitrary decision, which means that we have resonance structures here, right? Both of these are correct. So I want to go ahead and draw out both structures and understand that the real structure is a combination of the two. After that, I want to go ahead and calculate my formal charges. When I calculate the formal charges, I'll find that this oxygen here is negatively charged, and then this oxygen here is negatively charged. Is there a way that I could minimize that formal charge? No, I can't, because I can't create any more bonds to that carbon because it already has an octet. And even if I did, I'd put that negative charge on a carbon, which wouldn't be good, right? We want the negative charge to be on the more electronegative atom, not the less electronegative atom. Let's try to do the same thing down here with this structure that I've told you is not going to be correct. So let's think about what doesn't have a filled octet. Currently, this carbon right here does not have a filled octet. We've only got one choice. We've got to take it from this oxygen right there. So then our structure becomes this one right here. And then we have a lone pair right there. And now everything has a filled octet, so that's looking pretty good. Next thing we want to do is calculate the formal charges. Go ahead, pause your video, try to calculate the formal charges. What you should end up here is a formal charge here of -1. Formal charge here, let's see, 6 minus 2 minus 3 is +1. And then a formal charge here of -1. Right? So you can see that this structure right here has 3 separate formal charges. We've got a negative charge on a less electronegative atom and a positive charge on a more electronegative atom, both of which are not good. We've got formal charges right next to each other, which is also not that great. So for those reasons, this structure is not good and this structure is good. How would you know that? Well, that's something, again, that comes through experience and practice, which kind of leads me to this final point for this section of the video, and that's practice. You can watch as many videos as you want, but you're not going to do well unless you actually do it. So if you're worried that this is a lot, we will have a whole lab period where we're just going to practice drawing Lewis structures. So you have 3 hours there. Check out the extra resources. in Canvas to point you to some good online resources. Of course, you can use more online resources if you feel you need them. So you should get plenty of practice. If you want more practice, you can draw all of our structures for our polyatomic ions, except the ones that have metals in them. They kind of follow some different rules. So permanganate and then chromate and dichromate, you don't want to draw those two because those have transition metals. So they kind of obey different rules. But the overall theme here is in chemistry, we learn skills, not memorize facts. So you've got to learn how to do things, and the best way to learn how to do things is to practice doing them, right? You don't just want to sit there, watch videos, try to remember facts. You need to get in there, get your hands dirty, and get some practice.